Okay, let's go ahead and talk about flashover in compartments. Let's go ahead and drop a diagram really quick. This diagram represents heat release rate as a function of time. So all fires effectively can be modeled as power fires, your standard T-squared fire. For the most part, up to about 5 kilowatts, the T-squared fire is reasonable as a point source representation. So initially, you have an abundance of oxygen. And the fire grows and grows and grows until it simply doesn't have enough air to continue growing. And at that point, it's called ventilation limited. It just doesn't have enough air to continue growing. It has enough air continuing to come in that it has a constant heat release rate. And once that fuel then runs out or starts to run out, such as, for instance, a piece of wood that's charring, there's fuel there, but it's actually slowed down. So that becomes more of it's no longer ventilation limited, it's fuel limited. So you have an abundance of oxygen. At that point in a compartment fire, you go into this decay period. The purpose in understanding this profile for compartment fires is to comprehend the principle of flashover. Flashover is that transition during a growth phase where it comes up to a point, heats up a compartment so that the compartment, at least at the floor, has basically a 20 kilowatt per meter squared heat flux. And realizing the smoke layer that's basically formed at the ceiling, that's about 600 degrees Celsius. It produces a huge amount of radiation. That causes the items such as your chairs and your blankets and your carpet to ignite. Now typically the critical heat flux is on the order of around 12 kilowatts per meter squared. Flashover is determined about 20 kilowatts per meter squared. Flashover is the magic point that we need to identify and prepare for. So if we can have adequate fire alarm systems to notify people and means of egress systems to evacuate people prior to flashover, we can keep them safe. If they stay in a compartment after flashover, they will not survive. You cannot survive a flashover without PPE. So that's why it's so important to understand this concept and engineer a way out. So how to utilize this in terms of flashover? There's equations that Philip Thomas developed based upon the A sub T, that's the surface area minus the openings in a compartment, the opening area, A sub naught, and H sub naught, which is the height of the opening. M dot sub G is the mass flow rate of your air coming into that compartment. And since your mass fraction of air is always 23% oxygen, you can calculate how much energy is coming into the room. An important correlation is that your oxygen burn rate, regardless of fuel, is always going to be 13.1 kilojoules per gram of oxygen. So whether you're burning methane or hexane or wood, you can use this rule of 13.1 kilojoules per gram. So if you know your mass flow rate in, you know what your Q is through M dot sub G. So with that, your Q sub FO in this diagram can be calculated. So a lot of research has been done into things like, well, how much energy is released burning a chair, etc. So when you're doing a design basis fire, well, is the item going to ignite? And if it does, is it going to reach that flash over HRR, heat release rate, from Philip Thomas's equation on the former slide? If it does, then you have flashover and need to plan for it. If it does not, you have to ask subsequent questions, such as if the fire can spread, can it spread to an adjacent item and thus get to that threshold for heat release rate? So even though the item itself might not get you there, it could ignite other ones. If it doesn't, it's going to self-extinguish. If it does ignite other things, you have to plan for flashover. So going back, once you understand this principle, you can understand Philip Thomas's equations, that value, Q sub F naught, that value is your threshold for flashover. And we have the capability to evaluate that through your mass flow rate. What I wanted to emphasize by this graph was just the dependency we have on accuracy of our data. The data here that was used to derive the various models, Philip Thomas being one of those, is shown in this graph and the legend. It depends on data that's really not very good. And you're going to see that across the board with fire protection engineering. The models have oftentimes fairly poor accuracy, and that's why it's so important to have a safety factor. Safety factors typically used in engineering are 1.5. I know for egress requirements, there's actually a code-driven requirement for 1.5 for evacuation times, travel distances, things like that. As you can see in this example, having a safety factor of 2 it would actually be beneficial. So you have to really consider where the data came from in creating these models and just how unpredictable fire dynamics is. So keep that in mind as we go through, and if you ever try to evaluate a flashover heat rate, you need to factor in a safety factor there. Here's an example that takes you to flashover in about 3 minutes. Fire is initiated via a waste basket full of paper. What you'll see is the black smoke at the ceiling. When that forms, you know that there is significant radiation. Radiation goes right through oxygen and nitrogen, the main constituents of air. It's basically transparent. CO2, water vapor, those behave a little bit differently, but carbon-heavy, sooty smoke radiates significantly. And when you hit that 600 degrees Celsius at the ceiling with that soot, it radiates downward. So now that it's smoky up on top, take a look at what that radiation does. It pushes that 20 kilowatts per meter squared on the ground, instantly creating a flashover effect. That's the trigger for the flashover you see there. So this is just a side view of a compartment, just to demonstrate the principles behind flashover. What you have is your smoke mass is going up due to the forces of buoyancy. It's filling up this hot layer area at the top with this sooty, hot smoke that reflects back, radiative energy back. If you recall, your thermal radiation is proportional to the 4th power of the temperature in Kelvin. So significant increases in temperature create huge energy changes as far as radiation goes. So if you look at this whole system, this little itty-bitty amount of fuel, the ratio between your mass of your fuel and the mass of the smoke is about 10 to the minus 4th. So it's just this tiny addition of mass. But that little bit of mass creates this huge heat pump cycle relative to mass coming in and mass coming out, where M sub I and M sub O are basically the same. But the energy associated with that upper layer of gas is what creates that radiative effect that causes flashover. Okay, I just wanted to put another example. This is firefighter training. It's not the video I actually wanted, but I having to switch out the other one, which was the Bradford Stadium fire, with this one because of copyright issues. So this is standard firefighter training. What you do is you bring in a trailer, kind of like a big Conex box, and they just, man, I'm thinking it's actually, I think it's actually like a diesel fire or something they use inside of there with some kind of other cellulose-based combustible. So what personnel do is you don your PPE, go in a respirator. It really is not indicative of a real compartment fire in terms of flashover. It doesn't, because a flashover, the kind of we're talking about, involves full compartment involvement, and that would be your walls, your floor, etc. But this is interesting training. It makes sure that firefighters are not going to have any kind of panic attacks or anything like that. It's not really a requirement for Firefighter 1 qualification, but it's more of one of those things offered at the fire academies, such as Southern Idaho Fire Academy, CIFA, or East Idaho Fire Academy over in Idaho Falls in May. Um, so it's just kind of interesting. Nothing too exciting. I hear it's actually. I take that back. I hear it's actually exciting to be in the trailer. But all you're seeing is basically the fire rolling across the ceiling. That's where those black smoke layer forms. But since there's no other combustibles in there, you don't see that full effect of the flashover. So, okay, so I know I showed this in the past, but this is really interesting, I think. I just wanted to demonstrate in terms of flashover. It's not just so much the mass of your material. It's not even so much the heat of combustion of the material, such as kilojoules per kilogram. There's another factor, and that has to do with the speed of the combustion. So as you can see, interior finish, it falls into various categories. I know we talked about that in the past, but just wanted to demonstrate this before we moved on, that interior finish has, as far as its form factor, as far as the material properties, it has a powerful influence on flashover. And in this case, this is craft paper. The craft paper being that facing for insulation you frequently see in rooms that people have started to do construction on and haven't bothered to put the gypsum up to protect it. So that you can expect a very fast reaction here. And it's not a lot of mass. It's very limited mass. It doesn't take much for this kind of an event to occur. So just keep that in mind.
Okay, so I just wanted to show you how to actually implement your equations, how to actually perform the calculations. And what I think the videos that we've looked at here, what they show you is there's a lot of variability. And the reality is formulas associated with fire protection engineering, due to assumptions, things like that, really are only designed to get you about an order of magnitude as far as accuracy. I think even mechanical engineering, any engineering field, your target's about 20%. But fire protection is particularly challenging because the form factors of your material is challenging. So if you take a look, for instance, the common T-squared fire, which is defined by an alpha value. If you look at the alpha values, SFP Handbook of Fire Protection Engineering has it. This is a Drysdale document here, but look at the significant figures you have on these values. And the reality is when you're trying to guess values, you're nowhere near, 100,000th place. But these are standardized values. They represent pockets or themes associated with fire spread. NFPA 72, one of the annexes there, Annex B, has a section that gives a variety of alpha values and also T sub G value. T sub G is the time in seconds that it takes a fire, a form factor of combustible products to reach 1,000 BTU per second, which is 1,055 kilowatts. But typically, your T-squared fire relies on this alpha value, which is basically derived from T sub G. So if you look at the Phillips or the Philip Thomas formula that we previously discussed, the 7.8 times your surface area of a compartment plus your 378 times the area of your opening, like a door, times the height of that opening. And that gives you a threshold for your heat release rate, Q dot, kilowatts, your heat release rate at which you're going to have a flashover. Well, I just arbitrarily selected some values here. 4 meter by 5 meter room, fairly large, and a room height of 3 meters, it's about 10 feet high. My Q value becomes 725 kilowatts. So if I do my analysis on the form factor of material in that room, using, for instance, the Q squared value, if I continue to burn and have enough material in there at an alpha value of 0.0469, 0.0469 would be a fast fire, such as mattress as shown here, pallets. If I burn that for 2 minutes, I'm going to hit the 725 kilowatts, and I'm going to have a flashover. And I got a plan for that. This model here is the Alpert method using an Euler approach, which is a discretized integration. But these are Alpert's formulas that I'm using here. And if I carry that down to 700, what the value was for Q dot. So Q dot here is 725 kilowatts. That's flashover in this room configuration. You can plug in whatever numbers you want. If I come down here and find out when 725, we already know it's under 24, 124 seconds. But depending on the variables, height of the ceiling, things like that, my detector temperature is only 53 degrees Celsius. Well, if I'm using like 165 degree Fahrenheit heat detector or sprinkler head, which correlates to about 74 degrees Celsius, well, I haven't even gone off yet in terms of where I'm at, in terms of the fire. So I set this up a little bit differently here. Let me plug in some other values here to show you what I mean by that. So I had an RTI of 50, which is typical for, I believe that's I think that's a quick response head. 22 degrees, 72 degrees Fahrenheit. Let's make the height of this 10 feet, which is 3 meters. So I'll go 10 feet. And let's go see where we are now. So if I come down here again to 124 seconds, which is, they're about 725. I'm at 67 degrees. What did that demonstrate? I reduced the height of the ceiling. I went from about 4.5 meters, 15 feet down to 10 feet, about 3 meters. It shows you how much faster it heats up the closer the ceiling is. That's another factor you have to take into consideration. So in this case, though, if I'm sizing my RTI based upon a possible fire, the flashover situation at 725 or thereabouts kilowatts, well, I've already flashed over in this particular crazy case before my detectors got off. So I'm going to look for a temperature rating that's below this. In this case, it's 165 degrees. So I probably want to go with something a little bit lower. So this is how you approach things to get this balance in terms of how do you protect people by having a heat detector for a given fire design for your combustible loading. Now just to explain what this spreadsheet does here. So we're evaluating Q based on alpha T squared. In this case, using 0.0469, which is a fast fire. And then you use Alpert's equation to determine the temperature of the gas at the ceiling level, temperature or the velocity of that gas, and you use that to determine the temperature of the detector. Now, the faster that gas goes past that detector, it's like wind chill factor. Your velocity of your air affects it. So anyway, these are fairly standardized and well-accepted formulas here that I'm using. Point is, you're not technically in this configuration even going to trigger until you are at about 133 seconds. But remember, your Q value in this particular scenario for flashover happens at 124 seconds. So that's what you need to keep in mind. Anyway, I could go on and on. There's a lot of different values to play with. I want to show you this. This is a little spreadsheet put together to help understand heights. So if you're in a room, tenability, according to NFP 92, is defined as having a smoke level layer that's above 6 feet. Now, technically, Appendix or Annex A of the NFPA 101, Section 5.2.2, it gives you 4 criteria for tenability that you could apply. It actually, you're allowed to breathe smoke in, as long as you can prove that you're below a certain carboxyhemoglobin level, so that you are not incapacitated. You prove that, you could be in a smoke environment. You could prove saying, hey, you're going to have burnout in a room. You just don't have enough combustibles to justify fire spread before flashover. You can go that approach. Or you can go by the approach where you're never going to descend the smoke layer below 6 feet. So in this case, this particular compartment is fairly small. I just set this up. Your height is going to be about 2.75 meter. So it's a fairly small area. You know, that comes out to be about 8 feet tall ceilings. So in this case, you know, I just wanted to evaluate it. I mean, it'd be pretty fast if it went from 8 feet to 6 feet in the compartment. So in this case, I went down to 1 feet, about 1 meter, you know, about 39 inches thereabouts. So you could crawl out. And the time in this case, you know, I have 0.0029 here for my alpha value, which is a fairly slow. I mean, this would be like, you know, basically a bunch of rolls of paper or something like that, or stacks of newspaper, something like that. It just would not have the capability of pyrolyzing fast enough to create a fuel mass flow rate, those vapors, to go and you know, create a very fast fire. So in this case, if you had like a room that, in this case, what are we at? We're at you know, basically 4.75 meters wide, 3.5 meters long, and a 2.75 or 8 foot tall ceiling. You know, you're going to end up getting to a 1 meter height here in 96 seconds. So once you start that fire using those parameters with newspaper, and this would be common. I would say you know, if you're the trailers, this would be fairly slow for fire. It'd be a lot faster than this, but it would descend very rapidly. So that's another thing to keep in mind. So we talked about flashover, the other is tenability. I wanted to mainly focus on flashover. I don't want to get into this too much, and the whole purpose of this was to define that, or help define that. You have your Q dot using the Thomas model to show you what Q dot HRR is going to give you a flashover. You have the DTAC method for Alpert's equations using Euler's method for discretized integration. Not really an ideal model, but if your math skills are poor, it's the easier way to do it. So I think you understand there's a lot of things to balance. Interior finish would be one of those, as illustrated in the last video. In any event, that should suffice, and I'll just open it up to questions. So that should be good.